I'm now going to introduce to you a different way of looking at regression analysis. And this is talked about, discussed in your textbook near the end of the chapter. And I'd like to cover it because it introduces some ideas that we look at in chapter 11. So it's kind of killing two rocks with one bird. We can introduce it here, look at regression analysis differently, but that terminology shows up a lot in chapter 11, so it kind of helps us pick up that chapter. Anyway, that's what I'm going through this exercise. But another thing I like about this, it gives us an idea of why R, the regression coefficient, tells us what it does, and why R squared tells us what it does, and why R is between -1 and 1. So let's begin with a hypothetical set of data, XY data, and we create a scatter plot. So my x's are on the independent axis, my input axis. The y's are on the dependent or output variable axis. And I've got a plot of points. And somewhere in this is the regression line. And so here's the least squares regression line. Now we write this in the form y equals to a plus bx. That's the statistical form of a regression line. Well, I'm going to put one point kind of far off it, up here somewhere. So I have a lot of room to write, and it's easier to see on screen. So I'm going to focus on one point, but the idea goes for all these points. All right, now first of all, what is that line describing again? It measures the expected effect on y that x produces. So when you change an x, it does this to y. So for example, if I have a point here, if I change x by this amount, I expect y to go up by that amount, by the slope amount. And so regression line sort of measures an average effect of x upon y. Now, the correlation tells us how good that is, how close that fits. You know, if points are close together, normally we expect the regression coefficient, R, the correlation coefficient, to be close to 1, close to perfect. And if the points are real scattered about, then we expect it to be somewhat lower, somewhat weaker. So we can measure, how close we are by using by looking at the correlation coefficient. Now then, what causes the scattering of points? You see, not everything in y is related to x. For example, height and weight. If you had height on the x-axis and weight on the y-axis, you would see a positive correlation. Taller people weigh more on average, but individuals are going to be off that line because there are other factors in play. There's body type, there's diet and eating habits and exercise habits and genetics and all those things that make us different sizes and shapes. And so there are other variables at play that causes the data to scatter away from the line. If we all looked exactly the same, had the same shape, had the same body type, same metabolism, ate exactly the same things, then you could predict weight exactly by height. It would be a perfect correlation. But the fact that it's scattered away from the line means that residual variables are also affecting it. So the regression line is an attempt to measure that average relationship with x, recognizing that it's seldom if ever perfect. You seldom if ever see a perfect correlation. All right, now then, let's think about what y bar is. If you took the average of the y's, and let's suppose this is the average, y bar. All right. If nothing ever affected the y variable, if x didn't affect it, if no other residual variables affected it, then the y would be constant, it would be flat, because nothing causes it to change. Not x's, not anything else. And so I drew y bar here to indicate, well, what would happen if there was no effect on y by anything? Obviously, with this data plot, there is. And so, if I look at this measurement here, and that measurement is a y value minus y bar. If I go through and do that measurement all along here, if I construct these little vertical bars, I want to measure those distances, and then I want to square them because I want all the negatives to go away. I don't want negatives canceling positives. So if I do that and square those, that's called the total sum of squares. So the total sum of squares is literally the sum of all the differences between the y's and the average of y bar squared. Now, I don't expect you to do any of these calculations. Don't worry about those calculations. I do have one example to show you where I did those calculations, and I'll show that to you later. But this is TSS, means total sum of squares. And let me write out a definition here. Now, I'm probably not going to have room to write all my definitions, so you'll have to copy them and erase them later. I'll have to erase them off the board. So the total sum of squares, TSS, measures all effects on y, on variable y. Not just x. X affects y to some extent, but so do other residual variables affect it. So we call that the total sum of squares. We abbreviate it as TSS. So I indicated, geometrically with this segment, but literally you are doing this calculation everywhere, and you're squaring those numbers. Makes it easier to do the math to square those and get rid of negatives. All right, so that's the total sum of squares. Now, and again, that's the net effect of everything that changes y's. All right, now then, what makes a y value jump from here to the regression line? Okay, now that would be the effect of x upon y. And so this little, let's see what color. I'll pick orange, I guess. This little part here is called the regression sum of squares. So I'm going to erase here and write out the regression sum of squares. And our book abbreviates it REGSS. And that would be, symbolically, that would be the sum of the differences between y bar and the regression line, a bx, and then we squared it. Looking in the book, they may have that reversed. Yeah, I'll tell you what, let me apologize and just reverse that. It's probably easier to see if I flip these around. When you square it, the negatives all become positive. So let me write it this way: a plus bx minus y bar. All right. And I'm using a subscript here. The subscript just means that I'm going to account for all the x's. All right, so literally it's the difference between the regression line, y equals a plus bx, right here, and y bar. That difference, we take that difference, we square it, and again we do that all for every point on there. We square those up and add them up. That's called regression sum of squares. And so let's write out a definition for what that is telling us. The regression sum of squares measures only the effect of x on y. All right, so what if you had a perfect correlation? Remember what that means. A perfect correlation would mean that all these scatter points would be right on the regression line. They literally would be on the regression line. You wouldn't have anything away from here. And so in a perfect a perfect correlation, then x is the only thing that's affecting y. So the reason they jump from y bar to the regression line is because x changes y directly. And it's the only thing. There are no residual variables in that case of perfect correlation. Nothing that would cause a point to stray away from the regression line. So that would be a perfect correlation. And but that's what we're measuring here. So, well, if we had a perfect correlation, then this would measure all the effects of x upon y. All right, so that's what we're accounting for here with the regression sum of squares. Now then, the other piece is this piece right here. And let's see, my green pen's getting a little faded, so let's try with I used to have a purple pen. Don't know where it is. I just go with blue. This distance we're going to call the residual sum of squares. And I'll write that out like I'm doing the others. The residual sum of squares is going to measure the effect on y of everything but x. So in other words, if you had a perfect correlation, then the y's would jump to the line based upon what value x was. But because it's not a perfect correlation in this case, then they jump away from the line. So this distance away from the line is due to residual effects, residual variables, other than x. And so if x had total effect, you would have no distance here, it would be right on the line. But because there are other things affecting y, then those are the residuals. And so the RSS would be the sum. Again, you don't need to know this for formula purposes. It would be the differences between the regression line and y. Let me see how the book writes it. Now, see, he gets it, kind of turns it around. So I'm going to be consistent with what I last wrote and say, well, this is the difference between the regression line and the actual measured y value. And we square it. So here's the regression line value for y. Here's the actual value of y sub I. And we're going to square that distance so we don't have negatives canceling positives, and add all those up. And that's the residual sum of squares. So the residual sum of squares measures all effects on y by variables other than x. So all those other factors are summed up in the residual sum of squares. All right, so that introduces that terminology. Now we have similar terminology in chapter 11 to consider. It's not quite the same, but it's very close. And but now let's work with this. If we could calculate all this, then some amazing things happen here. I think I might have visitors, so let me take a time out. I'm back. I'm expecting visitors, some grandkids and so forth to come in, but they're not here yet. Heard something else. So where was I? I want to discuss what does this tell us? What does this tell us? Well, for one thing, it's kind of amazing, but it can be shown that the residual sum of squares, this is the x-axis, the residual sum of squares plus the regression sum of squares equals to the total sum of squares. So that's a kind of algebraic property. It looks obvious from this diagram, that these two segments equals total, but when you start squaring that stuff and looking at everything, to me it's kind of remarkable that that actually still holds. So the sum of these is the total, and that's good to know. Now here's where r comes from. It turns out, and because we're squaring things, I'm going to call this r squared. R squared is equal to the ratio of the regression sum of squares divided by the total sum of squares. So if I take the net effect of x on y, which is measured by regression sum of squares, and divide it by all the effects, total effects, I get a proportion. I get a fraction or a proportion. And we'll call that r squared. And that's where it comes from. When we say that r squared tells you the percentage of the data attributed to the effect of x upon y, that's where it could come from. It can be calculated this way. And literally, I think it's kind of easy to understand now. If you think about that, okay, well, here are all the effects of x on y. Here's everything. And so the percent attributed to x is this piece divided by the total. Regression sum of squares divided by total sum of squares. And then now as you can see, neither of these can be larger than the total sum of squares. They're always smaller, or at most equal to. And so, in other words, regression sum of squares cannot be bigger than total sum of squares. So that tells us that this fraction is at most 1. If you had a perfect correlation, it would be 1 because residuals would be 0, everything would be on the line. And so regression sum of squares would equal total sum of squares in that case. And because we're squaring numbers, that's greater or equal to 0. So r squared is between 0 and 1. And then if you take the square root to get r, the correlation coefficient r would have to be between minus 1 and 1. Because if you square these little negative numbers, you'll get positives, and that'll still fit into here. So that's why the regression coefficient is between minus 1 and 1. And why r squared is between 0 and 1. All right. So from here, we can do a hypothesis test on the whether the correlation is significant or not. And to introduce that, I'm going to go to a book example. So I'll stop this video and start a new one for that.